So today we're going to talk about representing motion. Here we have snapshots of the motion of this car. In the same amount of time passes between each snapshot. So if it's like 5 seconds, it's the same between this car and this car, or this snapshot, and then this one and this one. It's each 5 seconds between. Um, what it's showing us is how far the car is traveling in those time periods. So we can see in this example, the car is traveling the same distance in each time period. That's useful information. Let's look at another example, or well, I guess it's technically 3 examples. So first we have the skateboarder, and the distance between each of the snapshots is again the same. So just like the car on the previous slide, it's moving at a constant speed or covering the same distance in the same amount of time. Then we have a runner, and you can see this is when the runner's starting out. So their snapshots are closer together. So it took, or they don't get as far in the same amount of time until later once they get up to speed. Then you can see that there's much more distance in the same time interval. And so this person, they're speeding up. And then we have this car. And initially the car's kind of, the distance in the time interval is pretty big, but then it gets really small, like overlaps with its previous position. And so what that means is this is the same amount of time, but the distance is getting smaller. That means it's slowing down. And let's look at an example, and then I want you to try and answer this yourself, but I'll also tell you the answer in a sec. So we have these 2 snapshots, the red car moving to the right and the yellow car moving to the left. And we want to know which one of these is moving faster. The direction doesn't matter in this because we're just asking about the speed, how fast it's going. So the red car, if we look, in order to answer this, we also need to assume that the time interval is the same. So the red car, in the same amount of time, travels like half the distance of the yellow car. So that tells us that if we switch that around, the yellow car travels twice as far as the red car in the same amount of time, which means the yellow car is faster, car B is faster. We can also show these same motion diagrams using the particle model, where we just take out the like cartoony image of the object and just use a dot. This is something you could also draw yourselves. It'd be a lot easier than drawing the car one. So again, the same amount of time passes between these, and then the number would be like the order of when these were taken, because sometimes with motion, we know someone like could be moving to the right and then they stop and turn around and go back to the left. And so being able to indicate that would be useful. So this one shows us both the time interval and the position at these different times, like in feet, and we have kind of like distance represented by X or position represented by X in feet at the bottom there. But time interval is just a change in time or really a period of time. But if we need to do some math with it, we need to remember that change in is final minus initial. So if we need the change in time, if we're going from initial and to final, that would be 6 minus 0, gives us 6 seconds. And also if we want to look at our initial position here, which actually we're doing on the next slide, so let's go over there. And we can find the time interval, and we can find the displacement, which again, displacement is change in position. and time interval is changed in time. So the final position is 120 feet and the initial was 0. So the displacement over this 6-second time interval is 120 feet. So we can also, in this, sorry, just thinking of how to say this, what this is indicating is we have these vector arrows showing us that, the size, like just making it easier to see, I guess, the size of, I'm sorry, how much more distance it covers in the same amount of time. Sorry, that I don't know why that was so challenging. Anyway, but I think it helps as a indicator of like, this is also showing us that it's taking more speed to do that. So, I guess what I'm trying to say is it doesn't necessarily give us new information, but it indicates the information in a new way to help us also think about the speed. So that's what this is saying. It's saying, if for this one in 1 second, it gets to 40 feet, and this one, it gets to 20 feet, then this speed is going to be larger, represented by a larger arrow. And speed is the distance traveled in a given time interval divided by the time interval. So that would be usually our displacement divided by our time, which we found for that previous example of our time interval was 6 seconds and the displacement was 120 feet, which would give us, I think, 20 feet per second as the speed. So speed just tells us the size of that, like how fast they're going, what that number is. But then velocity is speed and direction. So velocity is a vector because the vectors have a magnitude, a size, and they point in a specific direction. So it is the displacement divided by the time interval, but we care about the direction here. If you don't care about the direction, if you're just like, that car is moving fast, you can say a speed. You can just say speed. But if direction matters, which it does for a lot of our stuff, we want to use velocity and indicate the direction. So in that example with the red and yellow car, velocity, one would be negative and one would be positive because one was moving to the left and one was moving to the right. So I don't know, you might be familiar with this language. I mean, we talked about vectors. I guess I did talk about scalars briefly towards the end of that lecture. But scalar is just the magnitude, just the size, how big it is, or how fast it's moving. And that's what speed is. Speed is a scalar. And then velocity is a vector. It gives us both that magnitude and the direction, so we know how fast an object is moving and in which direction. And then that's these vectors. So the blue is the displacement vector. That's that triangle X or change in position. And that has a direction too. It's the same direction as the velocity, or the velocity ends up with the same vector direction as the displacement. And so velocity is going to be, in most of these, is going to be in green, and displacement will be in blue. And again, if we want to think about these as those same sort of snapshots, so same amount of time, 1 second in between each. And then this is giving us an indication of the amount of distance. It's not set up so that we can take an actual measurement here. It's not giving us a scale. But we can see that, right, for these first 2 seconds, the points are really close together. The vectors are small. It's not moving that fast. But then they get much farther apart, so we know that it speeds up. So, this, was one way of representing motion, these, vector dot diagrams. But there's other ways too. We can represent motion in a table, or in a graph. Sorry, one second. Okay, but let's talk through the motion here. So what this is showing is a situation where a student is walking to school. So let's look at our particle diagram. This is the dot and vector one is particle. So initially it looks like she's walking at a steady speed because these are all the same size. But then it gets way slower. Seems like maybe she got distracted on the way to school. And so we have another, so this is minutes, not seconds. So we have a few minutes where she's not going very fast or barely moving at all, honestly. And then maybe she realizes she's getting late for school, and so she goes a lot faster, and it's faster than she was going in the first place. So that's what we can see from this representation, where again the green arrows represent the velocity vectors. We can also get that from the table. We can see that for these first 3 seconds, she moves 60 meters. And then, let me see, and then she only moves 20 meters per minute for 4, 5, and 6 seconds. But you can see that with the table, it's a little bit harder to see that, visualize the situation. It's very useful for doing some sort of calculations with it. But if you're trying to interpret it, it's harder in this. So you want to pick the best representation for what you're trying to do. So let's also look at the graph, because we can interpret the graph similarly to how we interpret the particle diagram. And this graph is position on the y-axis and time in minutes on the x-axis. And so what we can do is we can just, plot up those dots and see, okay, initially we have kind of a shallow slope. And then it's almost flat because that's when she's not moving very fast. But then we end up with a really steep slope because she had to start moving really fast. And really quick, I just am just out of curiosity, because she went 60 meters per minute, then 20 meters per minute, and then it looks like 100 meters per minute. So she was running very behind. So this is what we call a position versus time graph. Let's look at another one and just see what we can interpret from the graph. So this again is position. So we start at a position of positive 10 kilometers. So that means we are 10 kilometers to the right of our origin. If we imagine it's like this situation where we have our post office in the car. So it's 10 kilometers is, oh, I honestly am not sure what that translates to in miles. Let me actually just, no, we'll worry about it later. Anyway, it's somewhere on the right side. 10 kilometers. Okay. And then it looks like the distance gets smaller. It gets closer to the origin, which means that it's moving toward the post office. And that, yeah, and that gets us to, so it's moving to the left. And then when it gets to the post office, it looks like the car keeps going. And after 20 minutes, the car is negative 10 kilometers as its position, which means it's 10 kilometers to the left of the post office. And then, so this is 10 minutes because it's half of the 20-minute window here. So for the next 10, then the car ends up at 20 kilometers to the left of the post office. And then it looks like they stop for 10 minutes because the position isn't changing. It's just the same here. And then from 40 minutes to 80 minutes, the position is getting closer to the origin. And so that means that the car then turned around and is heading back toward the back toward the post office. And it will get there at after 80 minutes from when it started. It will get back to the post office because we see it's back at the origin. And this also talks through that. So at 0 minutes or initially, the car is, oh, I'm sorry, these are minutes. No, I think I was saying that. The car is 10 kilometers to the right of the origin, and then X decreases over this time, 30 minutes, so that we know that means it's moving to the left. And then for 10 minutes, it's in the same position, nothing's happening, probably stopped at a gas station, I don't know. And then at 40 minutes, X starts increasing again, indicating the car is moving to the right. And then finally, after 80 minutes total, it reaches the origin again, or the post office. Oh, yeah. So, well, this is bringing us back to the student walking to school, how at first she's walking at a decent constant speed, and then she slows down a lot for a while, and then she has to speed up a lot after that. So we can also look at more clearly at the graph of the motion now that we have the lines instead of just the dots. I think it's easier to see it here. But we can see how the slope of the graph is changing. So here's our initial slope, and then it gets shallower when she's not moving very fast. And then it gets really steep at the end when she realizes she's running late and she has to go a lot faster. And this slope, which is given by rise over run, is if we look at what rise and run are, rise, the y-axis here, is the displacement, and the x-axis is the time interval. Displacement divided by time interval gives us the velocity. So the slope of the position graph gives you velocity. And with that information, I mean, like with calculating the slope of the lines, you can then go from a position graph to a velocity graph. So we're not going to do the math ourselves, but for this portion of time, she's moving at 1 meter per second. So, and how that works for the velocity graph is this whole chunk of time from like 1 to 3 minutes, she's moving at a constant speed. The velocity doesn't change. So we should just have a flat line at whatever the velocity is, which is 1 meter per second here, for those first 3 seconds. And then this is when our slope changes, and this one is apparently like 0.3 or 0.5. I mean, sorry, 0.3 or 0.4 meters per second. And again, it's a straight line for 3 seconds. And then finally, for the last bit, you calculate that, and it looks like it's, I don't know, 1.6 meters per second for those last 3 minutes. Sorry, I think I said seconds before. So that's how you can go from a graph showing position to a graph with velocity just by calculating the slope of the position graph. Oh, and I think that is all of this one. So we're going to talk about this part, the graph specifically, more in class on Tuesday. But yeah, have a good day.